Hi there, this is Andrea with my Interactive Advanced Concepts for week 8. I'm going to be showing 3 different examples of supercooling with water. So I have some bottles of water that have been in the freezer. They're just about freezing. I can tell that some of it is actually frozen at the top, but it's still in a liquid form. So I'm going to go ahead and show the first example of supercooling with water. So here the water is in liquid state. I just got it out of the freezer. It's starting to freeze a little bit up there. And you can see that it's still liquid. And I'm going to go ahead and give it a force, and it's going to basically turn into ice really fast. So now it's all slushy. Yep, okay. With the second bottle, where's my bottle? Oh, with the second bottle, I'm going to pour the super cooled water into a cup. And drop some ice in it. Yep, it didn't work. Yeah, I think I just stirred from the water too much. So it basically separated out. The ice formed in the bottle, and then the rest was water. I guess it wasn't cool enough or cold enough yet. But I'm going to take that ice out and put it in there. And then my last bottle, I'm going to try to make a slushy. Oh no. I think I froze it already. Yep. It's not working. It's too frozen on the top. And I either left the water in the freezer too long, even though I thought it was liquid, but it wasn't. So it already kind of freezed, and I ruined the brink of when supercooling actually happens. And so to explain that a little bit is that at standard pressure, water freezes at 0 degrees Celsius. So it won't do that when supercooling is happening, and that is because it won't. What's happening there is that it's not turning into ice when it's actually at its freezing point. So even though it's below 32 degrees Fahrenheit or 0 degrees Celsius, it'll still be a liquid, which it shouldn't be. So you know, if it's a solid or liquid or a gas at constant pressure, it'll just depend on its energy. So the more energy it has, the most energy will be a gas, less energy will be a liquid, and the least energy will be a solid. So with the water, the molecules are slowed down quite a bit, especially compared to gas, and they're in a pretty loose order. But when you're even at that low temperature, the molecules are, you know, in the lowest, like, it's a lower form of energy. So they're still vibrating, but the bonds between them are really strong, so that's what keeps the molecules in place. So now the water needs 2 things to freeze, and that is it needs to be cold, it needs to have very little heat, and it needs to form a nucleus. So the nucleation site is where the water molecules will first arrange, where it will like become that nucleus that will eventually form that crystal structure of the ice. And then this is what the other water molecules will build upon when it's becoming that structure form. So the nucleation site doesn't just automatically happen. There'll either be like an impurity in the water, or it'll be a stimulation from an outside force. So basically what happens was that really cold water moves around and the molecules will arrange next to each other, and the water is able to start the process of turning into ice. So at this point, the liquids they're supercooled liquids are very unstable. When they're below freezing, the molecules want to form a solid. So when the manipulation comes in, like from the outside force of hitting the bottle or pouring it onto ice where it's already built upon, where there's already that nucleus happening, it's building, it will continue to freeze, like with the example of what was supposed to happen with a pile of ice. Or the same thing as when I put the ice into the glass of water, it was supposed to then create the rest of the crystallization structure. So that's what should have happened, but it didn't. But I'll probably try again after another couple of hours. But that's my presentation for now.